Hi everybody, this is lesson 6 of the kinetics unit. It is on the quantitative concentration changes and how we can, with this quantitation, we can actually determine relationships or functions that will relate the rate of a chemical reaction with the concentration of that reactant. It is by far the most tricky part of this unit, and possibly the most important, but also, only and also the last piece of this unit. So the rate law is simply an expression or a function that relates the rate of a reaction to the concentration of those reactants. So this rate law helps us to calculate the instantaneous rate of reaction when given the concentration of a reactant and the reaction constant. So this reaction constant is going to be a new concept that we have to come to terms with. But of course, we've been dealing with concentration of a reactant this whole time. So we know already that rate is essentially proportional to a concentration at a given temperature and pressure. So this is only true, should probably put a little caveat here that this is at a given temperature and pressure. So provided you know the temperature and pressure of your system, then you can you'll know that the proportion that you'll have a general idea as to the proportional relationship between these. So this proportion stays the same. I should probably say this at some constant at any given temperature and pressure. We can formalize this proportionality. So the proportionality we're talking about up here, we can formalize that into what is known as a rate law down here. And this rate law is rate is equal to some constant, the rate constant, K, times some concentration to the power of some exponent. And that exponent can have any value. It can have a value from 0 to whatever. In some examples, you might even have decimal values for those exponents. But most of the time, we will use, in this class at least, an integer-based exponent from 0 to 1. 0 to usually 3. So usually an integer from 0 to approximately 4. I don't see very many fourth or fifth order reactions that are out there, so I would say this is the highest values that we find. So the rate law describes how the tangent on the concentration time graph has a decreasing slope over time. That's really what we're describing. So if we go back to our concentration time graphs, we know that those concentration time graphs have some sort of decay to them. And if we were to take the tangent, the tangent to the curve at at different points throughout the time period of this chemical reaction, we would find that the rate is changing at some value, changing with some relation, and this relation would be through this function. So if we were to take these slopes here and we were to plot those all out, then they would make their own curve, which would relate concentration and rate. So for a given concentration, for a given concentration, we get a rate, and that rate will I guess it has to go through 0, will be some sort of line, assuming that this would be x equals 1. It could also be, they could, if we had x equals 2, hopefully you're kind of familiar with your x equals 2. You could even have x equals 3. Whoops, that's not how x equals 3 goes. How would x equals 3? Oh, yeah, it would look pretty much the same. Just kind of go like that. And they would be tighter and tighter, and they'd go higher and higher. So x equals 3. And so we could have all these different values, and these would all of these would be described by some sort of rate equals k times a. Here, 1, 2, 3, 4, 5, whatever. The order of a reaction, therefore, is this value up here in the corner. It is the exponent, and often we will relate the order of a reaction as the largest exponent for that reaction, or occasionally we might ask for the overall order where all exponents are summed. Yeah, so I think actually the order of the reaction, it should be the value of the exponent for a particular reactant, or might ask for the overall order where all the exponents are summed. Yeah, that's better. Okay, so let's look at some examples here. So for this this example down here, we have a chemical reaction. Maybe what I might do, I did a lot of work in here during our class, but I think maybe we'll take a clean break. How about that? For this video, we're gonna erase the whole thing and take a clean swipe at it. So hope nobody was too attached to that explanation. So we are given a chemical reaction, and the first step that they're going to ask is they want to know what is the rate law. So the rate law follows this general format: rate equals some constant times the concentration of the two reactants raised, or as many reactants as you have, raised to some powers. So in our example, we have two reactants and we have a rate. So we said the rate is equal to K times our first reactant, H2O2 or peroxide, raised to some power, times HI raised to some other power. In this example, we are always going to assume that we do not know the powers of this reaction, nor do we know the K. So we always have three unknowns, 1, 2, 3 unknowns. And we have to use the table of data to figure out what these unknowns might be. So we're going to go through the full explanation, or the full method first, and then we'll move to the faster methods afterwards. So for the full method of solving this question, what we want to do is we want to take the ratio of two rates and then use the ratio of two rates to determine the value of x and y. And the reason we do this is by choosing a ratio method, we can eliminate the constant k. So we're going to let's call this long solution. Take ratios of the unknown equation using data from two trials to eliminate variables especially k. All right, so what I mean here is we're going to take this equation, we're going to take this whole equation here. I'm going to copy that. I'm going to paste that. I'm going to paste it twice, like this. And I'm going to take this equation and I'm going to take a ratio. And what that means is I'm essentially going to divide this experiment here and do a little bit of cleanup, make this a ratio. So this is the ratio. And then I'm going to I'll shrink this, so that's a reminder. And then I'm going to take two different trials. So in this case, I always recommend you take a trial where the rate is larger and put that on the top. So here, this rate is larger than this rate. So let's put those in that order. So we're going to go sort of trial 2 over 1 and trial 2 over 1. So rate number 2 is 0.0152. And the rate at number 1 is 0.0076. Now notice earlier, over here once we started dividing, notice that we don't know what k is, but it is the same. So it removes itself. It negates itself, and we end up with a value equal to 1. K divided by k is always going to be just 1. And 1 times anything returns the same value. So we don't have to worry about the k in this case. So we get to actually take the k out of our new reaction we just made, our equation. Okay, now I'm going to replace the concentration values. So I'm going to take trial 2, which was 0.10, and trial 1, 0.10. And then I'm going to take the concentration values for the other equation, for the other values, so 0.20 and 0.10. So these are the same, these are just these values over here and over here. All right, same idea as what we did with the k. Here we have, look over here, we have 0.1 to the power of x divided by 0.1 to the power of x. Well, those have the same value, so they negate each other, and they can be removed from our overall equation. So I'm going to now do some division here. I'm going to get a value of 2 from those. And then I have something interesting here. So if you know your exponent law, then you know that if you have the same exponent but different bases, you can divide the bases but keep the exponent on the outside of the brackets. Oops, and that's a y. Like this. So we can divide the bases while keeping the exponents the same, but putting it to the outside. This value here is going to create 2 to the power of y, and then there's 2. So we have a rate is 2, but the only change was doubling, and that was hi. So if the only change was a doubling of hi, and the result was that the rate increased by 2, then that means that there is a direct relationship between the increase in hi and the increase in rate. A direct relationship implies that the exponent that is affecting that 2 has to be y equals 1. Okay, there's a direct relationship. Okay, so now we're going to do the same trick, only now we know why, and that saves us a couple of steps. So I'm going to take the same deal. I'm going to steal this thing here. Oops. Add, undo. Duplicate, move that down. Do a little bit of cleanup on here. Get rid of that. We can even clean this up. We now know that those y's are 1. Okay, so this is going to be step 1. This is step 1. Here we're on step 2. So step 2, we're going to replace. Now we have to choose 2 different ones from 2 different trials, but we still want to focus on, we want to focus now on H2. So I'm going to actually try to pick 2 trials. It doesn't really matter too much which 2 we pick, because we do know the value of y, but I'm going to pick 2 where that we haven't used before, and also one where we see a change and we see the same, stays the same. This is going to be really key to doing the faster method later. And we're going to get a lot of repeat here. I'm going to clean up all this. I'm going to put the large one on top. You know what? Maybe I'm going to make a mistake. I'm going to purposely make a mistake. I'm going to put put them upside down. So I'm going to put trial 3 down here. This is going to be my 3, and this is going to be 1. So 3 is on the bottom. I've got 0.20, 0.10, 0.10, 0.10, okay, and 0.0076. We get to cancel away these values that are the same, or negate them. And then I'm going to complete this division. I get 1/2 on this side, and I get 0.10 divided by 0.20 raised to the power of x. This is the same as writing 1/2 to the power of x. So what is x equal to? Well, for the same reasoning, having the rate is halved, or the trial 1 has half the rate of trial 3, and it has half the concentration, so it is a direct relationship, so x must be 1. So this leaves us with our rate law that rate equals K times H2O2 times HI. And they're all raised to the power of 1. We don't write the ones, but you could if you want. And that would be the end of that question. In the next example, I'll just read through it a little bit, but we're going to be able to figure out K. Now that you know the entire equation, you can go back and you can figure out K by plugging in these concentration values. Now the fast route of this that I explained in our live stream was if we look at the data table, we can find sets of trials where things stay the same. So this is same, and things are different, times 2, and then compare those to how much change there's been in the rate, times 2. And in this relationship, we should be able to find that 2 to the power of y has to be equal to the same 2. So all we're doing is finding the value in the table and then comparing them, and then the difference has to be that value of y. Do this again, but do it with the ones where the data stays, where we find the other ones stay the same. So this is times 2. This one is the same. And then this value is times 2. And so we would say that the 2 to the power of x has to be equal to that 2. And we can kind of put an x up here, we can put a y here, and then that can kind of remind you that it's 2 to the power of x has to be equal to 2. So let's go to the next one where we're going to find an example where the values are not the same. So I'm going to go over that. I want to show you that data, that sort of quick method right off the top here. So I'm looking at my table and I notice that there is one set that are the same. And this is going to be y and this is going to be x. And this value is times 3. And then I go over here and I notice that this is times 9. 2 goes into 18 9 times. So this means that I kind of go over here and I go, okay, so 3 to the power of x, right? That's what that's what I'm kind of making a little arrow here. And then must be equal to that 9. So this is concentration effect on rate. So in this case, what is x? Well, 3 to the power of 2. X equals 2, because 3 to the power of 2 gives us 9. Okay, and then let's go and look at, let's change colors here. We'll use green. And now we got some problems, because this fast method is not super great if there's lots of changes happen. So here we have times, oops, not times 3, times 2. And here we have times 4. And the total result is times 8. So let's see if we can figure that out. We have 2 to the power of x times 4 to the power of y equals, oh, not 4, 2. Another 2. 2 to the power of y equals 8. Except, what did we just solve for? X equals 2. So let's go in and fix that. So here's our 2 from before. Bring that in. And so now we can kind of do a little bit of logical deduction. We can realize that 2 to the power of 2 is 4. 4 times 2 to the power of y equals 8. So 4 times 2 to the power of y equals 8. So that must mean that 2 to the power of y is equal to 2. Divide away the 4 on both sides. And that means that y has to be equal to 1. So that's our shortest method possible, is by using the table. You do not have to use that. I worked through this on the live stream, but if you'd like to, I'll read through this example. I don't want to redo it, but this is another approach. It's essentially the same approach. Here I punched in the numbers. I kind of set up the table a little differently because I like the sort of modular nature of this kind of setup, of setting up your K's are over here by themselves, the A's are by themselves, and the B's. I set that up right away. And you can extend this as many as you want. If you have 3 reactants, you can have A, B, C, and have X, Y, Z. If you have, 100 reactants, you'd have 100 letters. I don't know what letters you'd use there, but anyways. And then we divide it away. Anything that was divided to 1, we can just get rid of. And anything, or any bases that divide to 1, you can get rid of. And then we just have to compare the other ones. But you can see that this is a lot more math than using the table method. So this rate here will apply to, this rate law applies at this given temperature and pressure that this experiment was taken. Remember that temperature and pressure do have a big impact on the rate of the reactants. Also, if they change the form of the reactants, so if they changed it to an aqueous solution, or they used crumbled up powder, or they changed the reactant size, that kind of stuff, then we would also have problems as well. But they didn't do that in this case, so we're all good. This is the example of determining the specific rate constant. So what we did was we took a trial, whatever trial. This one we used trial 1 in the video, in the previous version of this video, and that's supposed to be a 1. And we just punched in the value for rate, right? So this is the rate, this is the value of A, this is the value of B, raised to the appropriate powers, multiplied out, divided out, and we ended up with our overall rate of reaction, or overall rate constant. So this is the specific rate constant, and we have to include that specific part because this is only constant at the under the given conditions. Only constant under current conditions. So if you change the experimental conditions, you will have a different process. Here's one with 3 letters. Or 3 different concentrations. I show you the table method here, where in the 3 different colors, and you can see me working through that. So I identified, I believe I did the blue one first. So I identified that these 2 were constant and these 2 were constant, so we can ignore them. So then we only care about this 2 times increase and this 2 times increase in concentration, 2 times in rate. So that means that the power must be 1, or the order for that reactant must be 1. If we then compare this setup here, these 2 are constant, but there's a doubling here and a quadrupling there. So that means that this doubling leads to this quadrupling. So the order must be 2 with respect to B. And then the next one was really interesting. This is something weird that happens occasionally. So if you compare this one, they stay constant. This one, they stay constant. And this one, they're doubled, but the rate stays constant. So this is a very peculiar situation where the rate is constant. So you have an increase of the base by 2, but the value is 1. So what is the value of the exponent? It is 0. So that's a very peculiar answer, but it does have a lot of interesting implications. One of those implications comes from our last lesson, which is that this implies that C plays no role in the rate determining step. We could put a little S on that in case there's multiple steps. Determining step. Yeah. And this means that it has a role in the stoichiometry of the reaction, but its concentration has no effect on rate of reaction under these current conditions. Now you could change this if you played with this experiment a lot. You might be able to add a catalyst, and if you added a catalyst, it might interact with this reactant C, and then suddenly reactant C, which is necessary for completing the stoichiometry of the reaction, might become the most important step. Who knows? Now, there is one little statement here that I think a lot of students will skip over because it's not really on its own page, but it does play an important effect in the when you're talking about these mixing this process with a rate law or with a reaction mechanism, like in our last lesson. So for the elementary reactions, such as this one, if it's truly elementary, where the reaction happens in a single step, then the coefficients will become the exponents. But this is the only time this happens, and it is a very rare case. So if this is an element, so for example, if this ozone and nitrogen monoxide reaction is elementary in nature, then the coefficients of the nitrogen monoxide and the ozone will become the exponents, and those exponents will be 1 in this case. This is an exception, not the rule, since most reactions follow a multi-step mechanism. But this also does give you a tool for determining whether a reaction was a multi-step mechanism or not. You could balance a chemical reaction, perform a rate law determining chemical process or lab experiment, and then take that experiment and use its results to prove whether or not the reaction was elementary or not. And you might find that it is, or you might find it's not. So the first assumption you can make is to try to fit your experimental data to a model that assumes an elementary reaction. And if it fails that model, then we could move to determining the possible reaction mechanism from that point on. Okay, so there's some practice here. I went through and did complete all the practice questions, I believe. Oh, I did leave one behind. So, I left a couple. So let's do one practice question so that we have one that's fully worked through. And this one looks like a nice tricky question. So let's see how it goes. Let's approach it from a full perspective. So I'm going to start by looking at my table for places where the data stays the same. So here's a set of data that stay constant. So I'm going to start there. So this will be trial 2 and 1. I always say the one that I want to put on top first. And I want to put the big one on top. So 5.94 divided by 0.66. Maybe I should put a generic equation in just so we can remind ourselves. So general, so let's put a general form. General solution. We're going to do something like this, rate 2 over rate 1 is equal to the, I like to set it up this way. I think this is where we're going to go anyways. Concentration of whatever A2 divided by the concentration of A1 to the power of x, and then just essentially you're going to multiply this as many times as you need with whatever letters you need. So this is a very generic equation. I'm just making something that you could use for any problem whatsoever. So this one would be B and B and C and C. You could even put like ... if you had more. This is Y and this is Z, etc. Not too many reactions that have more. So in our case, we have rate 2 and rate 1 being divided, and we're going to put our reactants in. Our reactants in this case were labeled X, Y, Z, but that's okay. And so X is going to be 1.35, because I'm going to do trial 2 on top, divided by, extend this, divided by 0.45 raised to the power of x. I'm going to do some more of these. Y, Z. You can see my writing gets worse as I zoom out, but that's okay. Okay, so in this first setup, we notice that because these are the same, we can cross those out. They all equal 1 because they're all going to be 1 to the power of something. And so we only care about the value for x in this case. 5.944, I'm going to need a calculator. So I'm just going to pull one up here. Okay, switch calculators, scientific, thank you. Clear. Okay, 5.94 divided by 0.66, and that gives us a value of 9 on this side. And then 1.35 divided by 0.45 gives us a value of 3. And so we have 3 to the power of x, What is x? X is 2. If you do not know how to solve these backwards, then try everything you can. So I would probably just go, if I didn't know this, I would go 3 to the power of 0. Okay, definitely not that one. And then I would delete it, and I go 3 to the power of 1. Oh, definitely not that. And then I go 3 to the power of 2, and I would say, there it is. So it's 3 to the power of 2. We're always going to have an integer in this examples that we do in this class. Okay, so all I want to do is I want to repeat the process 2 more times, essentially, except I'm going to do some replacements where I need them. So, for example, I'm not going to use trial 1 and 2 anymore. I'm going to use 2 other trials, and I don't know what they're going to be yet. Let's go see. Okay. But I'm ready for action. So I see that 0.45 is a common theme for this next one. So let's see if we can find one where, oh yeah, look at this. So the z stays the same, and the x stays the same, but the y changes, and there's a change in the rate. So let's put those in there. So that is trial 3 and 1. So 3. And I guess I started us off with green, so let's try going with green. So 198 over 0.66. And in the slot for x, I'm going to put 0.45. It is raised to the power of 2 now. Not that that matters. In this example, 60, 0.20, power of y. And then 0.55, but it's to the power of z. Okay, so let's figure this out. We're going to do some divisions and some canceling. We can, or negating. We can negate these, make them equal to 1. So let's simplify. 1.98 divided by 0.66 gives us a value of 3, and that is equal to 0.6 divided by 2, which is 3 to the power of y. So 3 to the power of y, what would that be? Well, that must be y equals 1. Okay, repeat. Rinse and repeat. Duplicate. Second last calculation for this question. Clean it up. A little bit of cleanup here. Probably going to use that 0.45 again. We can replace that. We now know that this value is 1, so we can leave that empty. And let's see what trial we're going to compare. We want to use one where z has changed and everything else has stayed the same. So the only example I see is this 0.6 and 0.6 stay the same, 0.45 stay the same, but there is a change in z. And, ooh, what does that mean? Hopefully you're screaming at your screens that you already know exactly what's going to happen here. So 1.98, doesn't matter if it's x or y on top, but I will put the bigger one on top for z. So 1.10, 0.55 is power of z. 0.60, 0.45, 0.45. And that's everything set up. A lot of this disappears. All of this gets canceled out. I do put them in every time just because there are the occasional problems where I don't give you an option where you can cancel everything or you can negate it. Now, interestingly, this also is equal to 1. So we have a value of 1 equals 2 to the power of z. So that's 1.1 divided by 0.55. So that's 2 to the power of z. So z must be equal to 0. So our final rate law will be rate equals k times x to the power of 2 times y. And I am not even going to write the the z into my rate law because it has a value of 0. Or it has an exponent of 0, which means its value is 1. Now, does it ask you for the specific rate constant? It sure does. So let's do one last step, which is to punch in these numbers except for k. So I'm going to just use trial 1. That's the easiest usually. I'm going to leave a k in there. I have 0.45 for my x value. Square that. And I also have 0.20. And I don't have to put a z because the z would be raised to the power of 0. Let's see how this goes. 0.45 to the power of 2 times 0.2 times 0.2 gives us a total of 0.66 equals k times 0.0405. So we're going to divide that away. 0.66 divided by that crazy number, 0.0405. And we get essentially a value of 16. We only have 2 significant figures throughout, so we can actually only put 16. So 16 equals k. 2 sig figs. And that comes from up here. All of these have only 1, 2 sig figs. 1, 2, 1, 2. So not much we could do there. We were stuck with sort of a low significance answer. All right, hopefully that helps explain some things. I might sit here for another few minutes and do a couple more questions, but that is that. This is 3 and 4. Okay, and that's the process. So good luck out there, and we'll talk to you soon.